I just got my PhD degree last year, December, from Professor Yongjie Hu. Now I'm served as a postdoc in the same group. I'm working on the initial calculation on the electron and phonon transport. During my PhD, I developed a Monte Carlo code to simulate the transport of the phonons by considering the initial phonon-phonon interactions, which is beyond the relaxation time approximation. This code can be used to simulate the hydrodynamic transport process from ab initio. By the way, the four-phonon scattering is due to the higher order anharmonicity is also implemented in this code. I'm also interested in some new phonon transport physics, including the electron-phonon coupled transport and the non-Boltzmann transport for the localized vibrational mode through the Wigner transport equation. So today my topic is ab initio determination of new ultra-high thermoconductivity materials, the ternary compounds. So with the decreasing size of the microelectronic devices, the density of the transistors on the chip is increasing dramatically over the decades, which make the heat flux generated by the chips significantly higher. If you look at this figure, the heat flux from chips is orders of magnitude higher than that of the solar flux on Earth, rocket motor case, and even nuclear blast, and also even exceed the heat flux from the surface of Sun. The real challenge is that we need to maintain the temperature of the chips under the room temperature due to the application requirements. Therefore, to develop high conductivity materials are critical for heat dissipation. So here is the thermal conductivity of a range of materials. For most common materials, the thermal conductivity is on the order of 1 to hundreds of watt per meter per Kelvin. The standard high thermal conductivity materials in industry are silicon carbide, copper, and silver, which has thermal conductivity at 400 watt per meter per Kelvin. The conventional high thermal conductivity materials are prototyped by single element materials, for example, diamond. With the development of the ab initio theory, exciting progress has been made in searching for new high thermal conductivity materials for binary compound, including boron phosphide and boron arsenide. In 2017, the boron arsenide and the boron phosphide was found to have was predicted to have ultra-high thermal conductivity. This work was done by Lux Lindsay, David Guaido, and Thompson Renick. Later on, corrections based on considering higher order harmonicity was done by Tianli Feng, Lux Lindsay, and Xiu Ran. Based on the ab initio predictions, the high thermal conductivity of boron phosphide and boron arsenide are experimentally verified by experiments from our groups and other groups. Meanwhile, intensive studies has been made to search for high thermal conductivity materials on binary compounds almost over the whole entire periodic table. However, there's very limited materials shows ultra-high thermal conductivity for binary compounds, which exceed the 400 watt per meter per Kelvin. So now the question is whether such high thermal conductivity can exist in complicated crystal structures, perhaps the ternary compounds. So here we want to apply the ab initio calculation to explore the high thermal conductivity materials over a group of ternary compounds. So here is my ab initio calculation flowchart for thermal conductivity. This method can derive the material thermal conductivity starting from the electron wave function. So the electron wave function can be determined based on density functional theory, which determines the interatomic interactions. By treating the atoms as harmonic oscillator, we can compose the dynamical matrix based on second law of Newton and derive the phonon dispersion relation. Based on quantum perturbation theory, we can calculate the phonon scattering rates by treating the anharmonicity, defects, or isotopes as a perturbation to the harmonic oscillator. With all those inputs, we can solve the steady-state Boltzmann transport equation to derive the thermal conductivity. This ab initio method do not require any experimental parameters, phenomenological models, or empirical potentials. The thermal conductivity is a function of the phonon-specific heat, phonon group velocity, and the F function. Here, the F function measures the deviation of the phonon distribution away from the equilibrium Bose-Einstein distribution function, driven by the temperature gradient. This F has a dimension of the length, which can be effectively regarded as the traveling length of phonon between two adjacent scatterings. For most common materials, the phonon distribution is near equilibrium. Therefore, relaxation time approximation can be applied by assuming the background phonons are under equilibrium. But for high thermoconductivity materials, the temperature gradient can drive the phonon distribution far away from equilibrium. Therefore, the deviation of all the phonon modes should be considered simultaneously by solving the Boltzmann transport equation through self-consistent iteration. In Boltzmann transport equation, the heat flux driven by the temperature gradient is balanced by the phonon scatterings. So here I developed my own code which implements this iteration algorithm to accurately calculate the thermoconductivity for high thermoconductivity materials. So here's my calculation result. Here's a comparison between my predictions with the existing high thermoconductivity materials. This work is inspired by, among all the existing materials, the binary boron compounds, such as boron arsenide, boron nitride, and boron phosphides, has been discovered to have ultra-high thermoconductivity. And the carbon allotropes, such as diamond, has high thermoconductivity. So now I want to combine these two to search for boron-carbon ternary compound to see whether that can have high thermoconductivity. Let's zoom in on this red curve. The thermoconductivity of this predicted R3N BnC2 material has record high thermoconductivity at 2,200 watts per meter per Kelvin, which exceeding the recently discovered boron arsenide. So we did we checked the influence of the crystal structure on the thermoconductivity. We checked P4M2, PMM2, and R3N three-space groups. In P4M2 structure, each carbon bond is connected with two nitrogen bond and two boron bond. Each carbon atom is connected with two boron atom and two nitrogen atom. In PMM2 structure, each carbon atom is connected with the other two carbon atom and alternatively connected with the boron and the nitrogen atom. In R3N structure, each carbon atom is connected with other three carbon atoms and one boron or nitrogen atom. So from P4M2 to PMM2 to R3N, the number of carbon bond increases, which results in the higher thermoconductivity. Then we make comparisons among the elements in the group 5, from nitrogen to phosphorus to arsenic. With the increase of the atomic mass, the thermoconductivity decreases correspondingly. That is, the reason is that the increase of atomic mass can decrease the phonon frequency, as shown in this calculated figure. Since the phonon group velocity is the slope of the phonon dispersion relation, the phonon group velocity will decrease versus the increased atomic mass. Since the since the lower frequency has higher occupation number, the decrease of the phonon frequency can increase the phonon populations. The scattering channels for phonons also increases. Due to these two, the phonon scattering rates should increase with the increasing atomic mass, so overall, the thermoconductivity decreases. To quantify the number of these phonon scattering channels, we define the three phonon phase space for three phonon scattering processes. The three phonon scattering process involves the interaction among three phonon modes. This interaction has to satisfy both energy and momentum conservation, and based on which we can quantify the available scattering channels by three phonon phase space. Due to the fact that due to the nature of this delta function, the scale down of the frequency will scale up the three phonon phase space, which increases the scattering channels. Then we find with the increase of atomic mass, the phase space increases. The increases of the scattering channels further increase the scattering rates, as shown in this figure. To further investigate the transport physics in R3N BnC2, we calculate the accumulative thermoconductivity as a function of the phonon mean free path. The phonon mean free path is the average distance phonon travels between two adjacent scatterings. For high thermal conductivity materials, it usually has long Foner mean free path. For example, for boron arsenide, the Foner mean free path is on the order of 1 to 6 micrometer. However, if we look at BNC2, it has relatively small mean free path. More than 60% of thermal conductivity is contributed by the phonons with mean free path smaller than 0.5 micrometer. So why such high thermal conductivity BNC2 has short mean free path? The reason is that the key contribution to the thermal conductivity is from the large group velocity instead of the long mean free path. Group velocity is the propagation speed of energy carrier. From this figure, we can see for boron arsenide and silicon, the phonon velocity is lower than 6,000 meters per second. But for two-space group of BNC2, the majority of the thermal conductivity is contributed by the phonons with velocity between 6,000 to 18,000 meters per Kelvin. The high velocity of the BNC2 is due to the strong covalent bond and light atomic mass. Therefore, the reason of the high thermal conductivity in BNC2 is the high phonon group velocity. By taking advantage of the short mean free path, we quantify the size effect in BNC2. When the crystal size equals to 10 micrometer, the PMM2 BNC2 has comparable thermal conductivity versus boron arsenide. When the crystal size goes to 1 micrometer, the PMM2 BNC2 has double thermal conductivity versus boron arsenide. At 100 micrometer, the thermal conductivity of BNC2 is much higher than the thermal conductivity of boron arsenide. Therefore, the BNC2 still maintains high thermal conductivity when the crystal size is smaller than 1 micrometer. This is summary. In this work, I predict new high thermal conductivity materials in ternary crystals. I identified R3M BNC2 with a record high thermal conductivity up to 2,200 watts per meter per Kelvin. I investigated the high thermal conductivity origin in R3M BNC2, which has short mean free path and large group velocity. I developed fundamental understandings on phonon transport from ab initio theory. Here I would give my appreciation to my advisor, Professor Liu Jiehu, and all the lab mates and collaborators. Let me stop here. Thank you. I'm happy to have questions.
Questions? At least from what it looked like, the R3M phase was anisotropic.
Yes, it's anisotropic.
So which thermal conductivity were you reporting, and what was the conductivity in the other direction?
The thermal conductivity is for implant because let me show the structure here. Because at the implant direction, there's a lot of carbon-carbon bond which increase the thermal conductivity. The cross-plane one is on the same order with the implant, but a little bit lower. Yeah, I remember it's like 80% of the implant. Yeah. Question?
Did you consider the isotope effect in your BNC2?
Actually, I didn't consider the isotope effect. So what I calculated is isotope pure BNC2. Yeah.
So have you tried how much thermal conductivity will be reduced if it's natural?
If it's natural, then it goes from 2,000 to around 1,000.
Follow that. Do you have a sense of the comparison
Actually, the job should be different. For example, for boron arsenide, there's no much difference between the natural abundance and the isotope pure. Yeah. But for this material, there's a drop due to the isotope scattering. Yeah.
Okay, well, let's thank the speaker again.